Yeah, hello. So for the first part of the lab, we are going to create a notebook instance using Amazon SageMaker. So for this, over here and get to this part and click on this. Since I have already created a notebook instance and it's already in service, I'll go through another way to show you how to create a notebook instance. So click here on create notebook instance. Name it whatever you feel like. Yeah, as soon as you will see the status, and as soon as it will be up and running, we can move on with our next step. Yeah, so once it's up and running, we have to go here, open Jupyter. And click new and choose Conda Python 3. We used Conda TensorFlow P27, but for this part, we have to use Python 3. Okay, yeah. So as you can already see, I have already created a bucket. Oh, here I have already created a bucket with the required data which we are going to be using in our lab. Now, I found this tutorial here which tells us about how to import the data using the role or like whatever you want to do with it. So I'll be shutting this down for now, and I'll be using the code which I have already created. So here goes. Yeah. So as soon as you're here, run it. Yeah, as you can see, the data load was successful, and here, as you can see, we have our data uploaded here now. Now, I'll shut down this instance and we'll move on to the next part of the lab. Now for this part, so I'll start with the code which we have here. This is the code which we uh, did for the part one of the lab. Yeah, so this demonstration is for the first part of the lab. We use TensorFlow for our progression in this lab. I uploaded the data into my S3 bucket, which I have already shown you earlier, and retrieved it from the bucket as an input file. Code for that is here. And the data has four features: skewness, kurtosis, entropy, variance, and class, which labels them to be either genuine or be forged. We check the authenticity of the data after it is passed using head. Now we used info function to get the information about data set, such as type and total entries. Now we used describe function to get the information about the data set, such as mean, minimum, maximum, and standard values. We used pair plot by the Seaborn library to create scatter plot of the data set. From the plot, we can observe that the data is linearly separable and can be classified. This makes sense because skewness, kurtosis, entropy, and variance determine whether the banknote is fake or genuine. From the box plot, we can see mm, we can see that most plots are almost similar to each other, and uh, and therefore it's inconclusive. Only the variance graph does not look like the other graphs due to higher median, higher range, and higher number of outliers. The analysis and comparison of box plot with scatter plot provides a lot of more information about how the data relates to each other. Now for model order selection. Choose first 200 rows from each class. So 400 rows of data for test and 972 data for training set. As you can see here, 400 rows and 972 rows for 5 columns. We chose KNN algorithm for this. Now next create confusion matrix and plot the data. Now we increase the value of K for KNN by varying K from 1 to 900 in increment of 3 to find the optimal value of K. With this plot, you can see that with increase in K, the error increases as well for both testing and training set. Next, we perform logistic regression on the data set. Since the data is somewhat linearly separable, the weight vector can be explicitly retrieved and represent the separating hyperplane between the real and fake banknotes. The weight associated to each input dimension gives information about its relevance for the discrimination of the real or fake banknotes. Next, we are using k-fold validation to measure the accuracy on the test data with 10 folds. The shuffle option is utilized to randomly permutate the test and training sets. Accuracy of testing data is quite high at 99.16%. Even though it's quite high, we are going to attempt it again using different algorithms to see whether the accuracy will change or not. After analysis of graph for logistic regression, uh, as you can see here, we found the similar pattern as that of KNN. We observed that K is inversely proportional to rate of error. Now we prepared the learning curve and tested the data by scaling the value of K. We observed the similar results for as earlier for increase in K. We kept K constant at optimal value and started increasing the training set. We found that error rate decreases with increase in size of training set. As you can see here. Further, we plotted the graphs for training accuracy, testing accuracy, and loss against epoch. After analyzing all the graphs, we conclude that, like here you can see, increase in after analyzing all the graphs, we conclude that with increase in epochs, accuracy increases and loss decreases for both test and training set. The learning rate is used to find the global minima. If the learning rate is small, the model reaches the global minima with better accuracy because it is low. It is slow. However, if it is too slow, we might end up reaching the local minima rather than the global minima. For instance, before we tried the learning rate of 0.01, we also tried 0.001, but the accuracy then was around 68%, which is quite low. In next part, we created a new model with linear regression. Now compare expected and actual values. For that, we created a confusion matrix of true positives, true negatives, false positives, and false negatives. After analysis of graph, we found that error rate decreases up to a certain extent and starts increasing again after it hits optimal threshold value. For the final part, we created ROC curve for all the models used in the lab. As we can see, the line for each graph passes through the origin. Therefore, we can conclude that our model is good. Yeah. So this is it for the first part of the lab.
Hi, so I'm going to be demonstrating Lab 7 Part 2, and this is, I have already logged into the Jupyter Notebook homepage, and here I just want to show that the data has been uploaded in the system already, and this is the file that I'm going to be showing, Lab 7 Part 2. Okay, so let's walk through the program. The first part is just showing that Jupyter can run shell commands. And over here, we are importing the file earlier into the program through Pandas framework, which is like a data management framework. It can read a CSV file. And this is an example of the data structure, which is recorded in the raw data variable. So it has the header of the skewness, kurtosis, entropy, and variance. So we have added this manually through this line. And the data on the line below the headers, they are imported from the text file. So next, Pandas also supports plotting a scatter plot. So from the data variable, we just issue the function plot scatter, and given its axis with the column name, with its column name, and it can generate a graph according to what we need. You can also give like a label according to the type, genuine or forged, which will differentiate the color between the different points. So these are the results. And here, kurtosis versus skewness, and the yellow points represent 1, which is forged in the dataset, and purple represents 0, as seen from the color bar. 0 represents genuine in this dataset. And these are all like the iterations of the graph that we plotted. Every possible iteration. Okay, so next we are going to manipulate that data from Pandas framework into an array. And the way we do this is just issuing this function variable.values. And the reason that we drop the last column is because it is our result column, our label. So we don't need this in the training data set. X represents the training data, and Y represents the target data, which is 0 or 1 that we will try to predict. So in Y we will include only the last column as its value in the array, but X is everything but the last column. Okay, continue on. And in this block, it is going to separate the training data set and the testing data set. So according to the instructions, the first 200 rows will be the testing set for each 0 and 1 thing. Okay. And then here below this point is the code to do the machine learning. And I would like to give credit to these two websites which I have implemented their code. So this is defining data and target. So data is the input. So we have four features. As seen here, we have skewness, kurtosis, entropy, and variance. These are 4 features. And our output is one label, which is only 1 column. So accordingly, data is defined as a shape of 4 for 4 features, and 1 column defined as a shape of the target. And these are custom functions which define the weight and bias, and custom functions that define the layer. And I should continue running it. Okay, so in this model, I will deploy a neural network deep learning model which uses 2 hidden layers. So in layer 1, we define a custom layer which receives input from data here that we defined earlier, and it has 5 neurons. This is the number that we specified, 5 neurons. And in the second layer, we will receive input from the L1. L1 is the previous layer, and this will also have 5 neurons. And the final layer is the output logits here, and it receives from input from L2, which is the previous layer, and gives only one output. And here next we define the should run the program. Run. Next we define the loss function. Which is a standard loss function with the cross entropy. And then the learning rate, batch size, and iterations. This is the same as the epoch, or like the training generations. We have these are the numbers that we found to be good enough. And here is the optimizer. In our model, we are using gradient descent optimizer. And another thing is to just tell it to minimize the loss, which is defined the function as a function earlier. And here is the various metrics that we will use to measure the correctness of the model, which is prediction, correct, and accuracy. And we can measure like how good it is through this. Okay, so this is just to begin the TensorFlow session. And this is just a command to do it. And these are the variables that we will be used for collecting the accuracy of the model. So I think there are some errors over here, so I'm just going to restart the code and run everything. Okay, now that we have restarted everything, let's try to go through the process again. 7. Okay, and here's the training part. Okay, as you can see, it's running in real time, and we can see the accuracy and the F-score. It keeps improving with every iteration. So as you can see, at about 200 epoch, we have pretty good results already at 98%. And at 300 is 99%, and after 300 it's a perfect score of 1. So let's run this again. Okay, and here we can visualize our results by graphing the loss function over every epoch. As you can see, continuous improvements over time. And this is similar to above, but it's representing the accuracy. So it keeps improving. At around 100 epoch, it suddenly peaks up and keeps improving beyond until it gets to 1. And this is the loss graph. It's the same as above, but only up to the 200 epoch, and this shows like the growth period of the system. And finally, this is also up to 200 epoch accuracy, which better clearly shows the growth of the model.